Thank you, Karen. Yes, the next speaker is Gordon Dunsire. He's going to speak on RDA in library linked data applications. He's an independent consultant, formerly head of the Centre for Digital Library Research, University of Strathclyde, Scotland. He has also worked as a cataloger, systems librarian, and technical services manager. He is chair of the Joint Steering Committee for Development of RDA. He is also chair of the IFLA Namespaces Technical Group, a member of the IFLA Classification and Indexing Section Standing Committee, a member of the FRBR Review Group, and a member of the Dublin Core Metadata Initiative Advisory Board. His research interests are bibliographic and cultural heritage metadata, interoperability, and linked data in the semantic web. He presents and publishes widely at an international level. Gordon?
Thank you, Dorothy, and thank you to the conference for inviting me. I'm going to talk about an application of Ferber. It's called RDA. This is a librarian's application of Ferber, so I will fill all the gaps in that Karen very kindly left. So I'll talk about RDA in library linked data applications. I hope most of you know that last month the Joint Steering Committee published, after a gestation period of some 7 years, a version of the RDA element set. This brings together the attributes and relationship designators taken from the RDA text and element set itself. So I'm going to take that as a starting point. I'm going to talk about how these elements are tied into the Ferber model, what we can do about using RDA data in non-Ferber environments, including Mark 21, the semantic part of the semantic web, which is inferencing, maps, interoperability, and some issues that arise from this work. This is an Rdf graph. It represents a single triple that says that something with the URI RDAE P20037, it's meant for machines, not human beings. It has a label which has something meant for human beings. The English text has translator. And this is the basic declaration of the relationship designator translator from the RDA appendices. This is a graph, it's a triple. The subject is where the arrow points from, and the object is where the arrow points to. The arrow is a predicate or property. It has a definition. Everything in a square box in an Rdf graph is for human consumption. It's not for machine manipulation, and it cannot be linked to anything further. It terminates a particular chain. So here's the definition of has translator. This is just taken from the RDA text. Relates an expression to a person, family, or corporate body contributing to an expression of a work by expressing the original text of the work in a language different from that of the original work. It's not very pretty English, I have to admit. It gets worse. So that's another triple with the same subject, so we've conjoined the two graphs together. So we're now saying two things about this URI, RDAE P20037. This is for machines. We say that this particular relationship designator or property has a domain. That essentially tells the machine what kinds of things are assumed to be subjects of this triple. The domain, again, is a completely opaque URI. It's meant for machines, but in fact it's the class for Ferber expression, and we can tell that by looking at its English label. And similarly, we can class the range of this property. That is, what type of thing we expect the object of the property to have, and in this instance, it's a super entity, a combination of Ferber's person, family, and corporate body, which RDA has recently introduced, called agent. These things are semantic constraints. They tell you about the intended meaning and use of this property to represent real data. The domain and range limit the use of the property to certain types of thing, and the definition clearly is about what the property means. But I'll remind you again that the definition is not machine processable, although the domain and range are, because they link two URIs together. The definition is for humans. It's for programmers who can take this data and write effective programs to produce particular services, etc. The semantic constraints, therefore, are a mixture of human and machine inferencing. Human inferencing is a mystery to all humans. We don't know how we think. Sometimes we don't even know why we think. Machines, of course, are a lot dumber and therefore can think better, but only in a very, very, very limited way. So these semantic constraints are a mixture of human and machine stuff. When we put the element set out in January, we also included unconstrained versions of these properties. That is a version of this property which does not contain any reference to Ferber. It's generalized. It has no domain or range. But it does have a definition, and that was one of the issues we came across when developing this. We're trying to make the definition mechanically derivable from the original definition by replacing all references to FRBR entities with the word resource, which you can take to mean what ISBD means by a resource, and therefore what Mark 21 records are actually describing. The results can be fascinating. If the original definition talks a lot about Ferber things, as this one does, and we replace everything with the word resource, we end up with things that are barely understandable, but they are understandable by programmers. And it's just one of these issues. It has nothing to do with modeling and everything to do with practicalities and keeping costs down. We do not wish to maintain by humans a separate set of unconstrained properties. So we get relates the resource to an agent contributing to a resource by expressing the original text of the resource in a language different from that of the original resource. That can probably be compressed down to about 1/3 of its size and retain its sense, but that would cost money. We link the constrained property with the unconstrained property using a standard semantic relationship called subproperty of. And that relationship can be processed semantically by a machine. So if we take a data triple, not a model triple, but a data triple that uses that property to link something with the URI1 with something with the URI2, that can be expressed in human language as thing 1 has translator thing 2. But we can run an inferencing algorithm against this using the data on the previous page, the model. And a machine will automatically infer that thing 1 must be an expression because the domain of the property says it should be an expression. Similarly, that the object is an agent, thing 2 is an agent. So the machine generates additional information from that generic model map, actually in real data for our applications. And finally, it says the same thing as the first one, but with a subtle but enormous difference. That last triple, which is derived from the first one, is referring to a translator in a non-Ferber environment. So although it says the same thing, it's not got the same inferencing. That was showing how the JSC has attempted to bring together the tightly constrained and therefore quite powerful application of Ferber called RDA and get that data reusable in non-Ferber environments. There are very, very few real Ferber environments around, as Karen has shown. And there are even fewer within the library world. So what I'm now going to show you is a map between the concepts that are in RDA and similar concepts that appear in other linked data models used by libraries. So here is the basic relationship between a constrained and an unconstrained property. I switched to extent of text. This is an attribute property, not a relationship property. So we have a constrained version, constrained to manifestation, and an unconstrained version, and the arrow means subproperty of. There is internal structure, semantic structure, within RDA. Extent of text is a subproperty of the generic term extent. And we have this unconstrained parallel running throughout the RDA element set. So extent itself has an unconstrained property. And we can then say that the unconstrained version of extent of text is itself a subproperty of the unconstrained version of extent. And this little building block can now be used to interoperate data from RDA with other sources of data. I'll just bring in one further similar RDA example, which is really what we're beginning to call extent of expression. There's work going on within the JSC to develop this idea. Currently, we only have duration as a similar concept to extent of expression. And as with all of these elements, there is an unconstrained and a constrained version. These represent two disconnected Rdf graphs. There is a third well-known one, which is used extensively within and without library environments from the Dublin Core terms vocabulary. Dublin Core has an element for extent, and it declares it to be a subproperty of a more generic property called format. And for historical reasons, that itself is connected to what you could call an unconstrained version, the original Dublin Core. What happened with DC was that they decided that they actually needed to impose constraints on the original Dublin Core elements, and they called those Dublin Core terms, or DCT. So now we have three disconnected Rdf graphs, all talking about similar things. We can, of course, connect them, and we can connect them semantically. And this is where the importance of the unconstrained property comes in. The unconstrained RDA properties drop the Ferber attachment, the Ferber baggage. Dublin Core doesn't know what Ferber is. So in order to interoperate RDA data with Dublin Core, we've got to remove the Ferber stuff. And this is what this diagram does. The unconstrained versions can be directly linked to the concept of Dublin Core extent. And we can start filling the gaps in for all sorts of other bibliographic models and element sets. So ISBD has an element called hasExtent. And when you semantically analyze it, it turns out to be a subproperty of the RDA. This is quite surprising. But remember, we're talking about unconstrained versions, so there is no ISBD, there is no RDA in the RDA unconstrained version, there's no Ferber. The bibliographic ontology, which is used to store information about citations, can be connected to this graph. Bebo's number of volumes and number of pages properties are subproperties of the unconstrained extent of text. Unimark is developing an RDF representation, and we find that the Unimark tag 215 subfield A is also a subproperty of the unconstrained extent. And similarly, tag 127 subfield A is a subproperty of duration. Now that wasn't supposed to happen. It's decided to stop. The other part of that diagram was just tying in Mark 21, a Mark 21 equivalent of the extent property as well into the diagram. Yeah. So we can take that previous map, which is a conceptual or ontology map, and we can take a piece of real data, a single triple, and as before, use the map to create inferences from that data triple. So here we have something has extent of text, XV11323 pages in English. We can then infer that it also has extent with the same statement. But we can also say that it's also got an unconstrained extent of text, an unconstrained extent, Dublin Core Terms extent, and Dublin Core Terms format. So there are 1, 2, 3, 4, 5, 6 triples represented in the graph there. And they are all saying the same thing, but they're saying it in different languages of bibliographic description. So this produces interoperability entirely mechanically. Once you have the map, which maps different concepts together, then a programmer, and you don't have to be a genius programmer to do this, can write an algorithm that processes real-world data and outputs it in whatever format the application requires, Dublin Core, RDA, etc., ISBD. And similarly, we can take a Mark 21, tag 300, the whole tag, concatenate it together and say that some example has a Mark 21 physical description. But we can run that against the ontology, the model, the map, and generate 3 triples saying that if it's got a Mark 21 physical description, then it also has an unconstrained RDA extent and a Dublin Core Terms extent and format with exactly the same data in it. Issues, this is the last slide. There's a big issue with the interoperability of classes. If we tackle this issue, we can make those ontology diagrams more powerful. At the moment, we are just dumping the classes that are the domains and range constraints because we don't have a model between classes. For example, between ISBD's resource and Ferber's WEMI. And just to complicate things really badly, RDA uses a completely different definition of resource. It's semantically quite different from ISBD. So work has to be done on how these classes interoperate with one another. There is the synchronization of unconstrained properties that I mentioned. JSC does not want to maintain this parallel set of properties manually. It wishes to do it by machine and therefore has to derive things like definitions using mechanical transformations. As I said earlier, you end up with some peculiar results, and this is one of the the self-evident results in English, relates a resource to a resource that describes a described entity. It's massively redundant. But a human programmer can still make sense of that, I think. And the final issue that the JSC is beginning to look at is refining properties. I used the example there of has translator, but we can refine that property to say whether the translator is a person or a family or a corporate body, and there are well-known techniques for doing that, which actually just amount to adding more blobs to the graph. And that's it. Thank you.